Back. So in current lectures, what we'll do is we'll try to see the basic map visualization techniques. So under that, uh, we'll just see that to create maps, what are the important things which we need to consider while representing the geospatial data sets. So few of the, especially we'll look into thematic map classifications techniques. So what are the important factors which we need to consider while uh, uh, creating any thematic maps? So those are the things which we'll be seeing under this uh, lecture. So let's say first, why do we need a map visualization? So generally, the visualization process is being done, or if we say that any visualization techniques, basic objective of visualization techniques is that it should give a kind of insight of your data set. So like if you're having a large amount of data, which is in form of tables or data set which may be in a tabular format. So to comprehend that data sets, if we want to make a representation of those data set in a form of some visual cues, then what happens is this provides a kind of insight of your data. So generally, whenever we say the map visualizations, the basic objective of map visualization is that we should do some kind of representations which will ensure that there is a kind of cognition. So it should amplify or provide some kind of cognition. So that's the basic purpose of visualizations. Map visualizations is having the same purpose. So basically, it should give some kind of insight so that people should be able to discover something new, provide some specific explanations, and finally, once we know those explanations, then it should aid it as an should help in making some kind of decision process. So it's that's the basic purpose of any map visualizations techniques. So why do we need maps? I think almost all of us know what is the purpose of map. So it's basically the use of maps is quite evident nowadays, especially the maps, navigation maps are available in mobile phone. So it's now a part of our daily life. So it's basically for the sake of completions. I should say that it's basically provides a way to represent any kind of geographical data in efficient and effective. So it's, whenever we say efficient and effective way, means it has to use the optimum area which has been provided. So if you're having a paper-based map, so it should use all the papers in an appropriate way, efficiently, and as well as effectively. So it means that whenever you create any map, then it should be represented in such a way that the important features which as a map maker, if you want to highlight, that should be easily comprehensible by the map readers. So that's the meaning of efficient and effective way of looking geographical data. And basically, the most of the map, whenever we create, it will provide some kind of spatial patterns, or it will also provide a relationship, a trend. If in some cases, it will also provide a trend in a map. Most of the time, the spatial temporal maps, like the weather maps, provides you the trends of movement of, let's say, cyclone or any kind of spatial temporal phenomenon which keeps moving. So we can just have a look up. So it also provides a kind of trends. And in all these, basically pattern, relationship, and trends is one of the major reasons why we need a map. So if we see that the informations provided in a map is basically we look for two important informations. So one is the questions that where and what. So to represent these informations, we need to have, let's say in this example, is simply saying that where is the 30-degree temperature. So it means all the places which you see in a greenish area. So these are the places where the temperature is at 30 degrees centigrade. So that's what we can find out. So in which all areas which is available. And if we are interested to find out at a particular place, so let's say at a particular place in Delhi, I want to find out what's the temperature. So if I know the locations of a Delhi, I'll simply go to that locations and keep it into lookup table. And from this lookup table, that is nothing but the map of the world, we call it as a legend. So once we have these regions, we can easily find out that what's the corresponding temperature in the particular locations. So map provides these basic answers, and this is actually especially true for two-dimensional maps, like paper-based maps, whatever we have. It provides that informations. We are also having nowadays the geospatial web-based environment where there also we can get these two answers. Then there's also a third attribute. Apart from where and what, we are also interested in finding out when. So it's like the temporal component is also being put in. And in that case, we would like to know that in case of lowest temperature, when it is going to occur. And on the basis of that, we define different seasons. So it gives you the kind of, this map simply shows the distribution of temperature in a different season, or in terms of time, we can call it as a when. So at different season temperatures, we see the different distribution. So in case of winter, we see the largest or the basically the highest and the lowest temperatures to be quite low compared to what may be the least temperature in this summer. So this also is an important aspect which map is supposed to provide that information as well. So whenever we want to create a map, so generally in geographical data set or geospatial domain, you'll be having these three informations: what, where, and when. So if we create a map only on the basis of what, that is means the attribute, then we call it those kind of maps as a thematic map. We also have a kind of locations where, so it means like when we want to find out a particular location and values, and the particular geographical locations is quite dominant. In those cases, we call it, and if your map is mostly depicting the features, where is, what, and a lot of special features which is quite dominant, in those cases we create a topographical maps. We can also have a temporal map, as we have seen. So in case of temporal maps, we need to have a multiple snapshot maps that gets generated for each time period, and then we do the comparison of those snapshots to identify or find out a few specific temporal phenomena. So in all the cases, you'll be having these two data sets which will be a part of any GIS domain data set. So those GIS domain data sets may come directly from observations. So for example, your rainfall observation data may come directly from satellite data sets, or it may be derived after carrying out a few analysis. So you carry out few vector or raster vector spatial analysis, or you have done some kind of spatial modeling. So based after that, you get data sets, and that in all these data sets, these attributes, all the data set is going to have any one of these three attributes. At least for to create a map, minimum to what and when, what and where is required. Temporal can be considered to be one of the snapshots. So if you see in all these maps, generally we need to have a set of data sets. That's the data set which is the outcome of any uh, uh, geospatial analysis or measurement. So broadly, as we know that we can categorize the data sets either categorical or quantitative data sets. So it means we are having two broader category of data sets. And then further categorical data set may be a nominal and ordinals, and the quantitative data sets are interval and ratio. So I hope that you know the part of the differences between this, but let's me just summarize that. In nominal cases, different attributes may just represent the differences. So it means using the nominal data sets, we can differentiate the two different uh, features. We can differentiate between them, but we cannot find out which is or any kind of ordinality cannot be created. For example, let's say if you're having a different country's name which is available to you. So in that case, the different country name along with its border may represent only a way to distinguish a specific portion of geographical area is different from the another country. But we cannot say that this country is having a higher order compared to compared to another country, or maybe any other administrative boundaries. So in such cases, the nominal data set's basic objective is just to differentiate, and it puts all your data sets at an equal footing. Where in case of ordinal data sets, you may be having some kind of hierarchy, but those hierarchy will be a categorical basis, not on the numerical basis. So means you can do some kind of comparisons that, okay, this is better than this, or this is better than this, that kind of thing. For example, let's say if you want to say if the whole world is being divided into higher income group countries, lower income group countries. So if you want to find out, okay, higher income group countries, no, it means that their per capita income will be higher compared to the lower per capita income group. So these kind of things is basically provides the only, even if you're having a letters or the words to distinguish the values, but you'll be having some kind of ordinality based on the semantical meaning of it. Then we having quantitative or interval ratio, and these are the data set which mostly we use it. So interval is going to give you a differences. So we can say that some value is 10 more than 10 compared to other. For example, let's say we can say the temperature in Dehradun is 5 degrees lesser than the temperature in Delhi. So that kind of comparisons which we can make. So that's basically an interval data sets, and the ratio data sets is basically giving some kind of multiplying it. So we can, if your data set is having some values where we can say it's a 5 times, 6 times, 2 times kind compared to the other location and values, then the data sets is quantitative data sets. So in geovisualizations, all these data sets has to be mapped accordingly to corresponding visual structures. So the way you are having a different visual structures to represent graph or chart or something like that, those kind of things also can be combined with your geospatial information. So it means that you're going to have lat long values attached to some kind of categorization, classifications, or grouping of your data sets, which can be represented visually. And finally, you represent it in form of map. So this is the basic process of the geovisualization maps. And once we create these maps, then it starts providing a lot of, or it just starts, if somebody looks into those maps, then there might be a lot of questions maybe raised in. So it's basically, it amplifies the cognition. So this is just an example of population density map. And in this case, as we can see that once we represent that how the population of the world is distributed across, then in that case we can easily see that there are few zones which is high population density area, and there are few places where the low population density areas are there. So then there might be a lot of questions can be asked. Okay, this is just an example that most of the peoples are living in the Asian subcontinent. It means the population in the subcontinent is quite high. That gives the kind of representation of these informations, and then we can start looking into some wider aspect. But why is it so? Or maybe let's say in Africa, why the area, the northern Africa, we are having a very less population density, but suddenly after a zone, we are having a very high density starts, population density starts increasing. So we know the reason for all those like climatic reasons was there, the socio-economic reason, there's a cultural reasons, and so on. So there are wider aspects which we can easily link in, and we can make different conclusions once this information is being represented. So generally, you see that the basic objective of visualization is that, or geovisualization is that you put it the informations in a spatial domain in such a way that it raises and correspondingly also tries to answer the few of the questions. So this is just an example of population density map. As we see that there are large, very high population density, but in the northern African continent, we see there are very less population density. Similarly, in the case of South Africa, South America, and North America, and so on, and as well as Australia continent and other places as well. So mostly the southern continent is having highest population, northern continent is having or areas is having highest population compared to the southern. So we can make a lot of conclusion based on these. We can raise the questions and then finally we can start looking into the answers. So this in the current context of Earth, in Earth, we can easily figure it out that this is the reason why the population density is lesser and so on. But in some cases or some places, especially the phenomenon, even if you don't know, but this will immediately raise a questions and we'll be able to start looking for the answer for those. So in all these map visualization techniques, you need to have two basic elements, that is the locations and attributes. Those has to be there, and correspondingly these informations has to be linked to an appropriate representation. So once you do a proper presentation of these informations, we can provide an effective 2D maps. So in nutshell, we can say that generally the map productions will require some kind of data collections. So those data collections or spatial data sets may come from different surveying or directly by carrying of surveying or at a particular locations. Then you also attach an attribute which can be combined together. And once we want to do a representations, then that the cartographic design principle needs to be followed, which basically says that you have to effectively use the different cartographic tools like color, tone, textures, and so on in such a way that it gives the appropriate representation of data sets which is suitable for your users. So there are different type of maps. Broadly, we can categorize topographic maps. So this is basically fully dominant with the topographical informations of a particular area, giving details. And basic objective of any topographic map is that it provides or associates any geographical phenomenon to a particular place. So if somebody is interested, let's say, that wherever we are seeing in the low-lying area, so this low-lying area or the the coastal zone areas at a different depth and height. If you want to find it out at the different distances, then we can easily look into the maps and we can say, okay, these are the areas in the India locations where we are having a geodetic height of 30 meter or 75 meter or something like that. So those are the areas which can we can easily look into that. So basic objective of topographic map is that it provides the few phenomena and directly links to the locations. That's the topographic maps. In case of thematic maps, what happens is that you would like to provide an informations about a particular theme. So like in this case, we are seeing population density in a country wise if you want to see, and that can be represented, especially in terms, this basically shows the urbanizations which has occurred in a different countries. So if you want to see all those informations, so that can be represented in form of thematic maps. So there are other examples like weather maps, demographic maps, and so on. So let's say that an example that when we want to create a thematic map, how do we represent the data sets? So this is basically the different wards of Dehradun area. So it's basically a municipal boundary area. Within that, you are having different wards, and there are few informations available to you. So if I just put the informations in this way, where each of the individual polygons has been assigned color according to its own unique values. So, like in this case, what is we are representing? We are representing the information of population density in each of the wards. If you want to represent the information like this. So once this map, this information is being represented, it's very difficult or comprehend what exactly we are trying to show in this. So we are at max somebody, if I give this information or maps to someone, then he or she will be able to tell, okay, there are few polygons which are distinct from one and another, but what is the values, how is it related, and all those things are not possible to find it out within this. So it's basically randomly assigning the different colors. This is also use of cartographic tools, that is the color which has been provided or properly colored in each polygon, but it is providing a very less information. In fact, it is not providing any information apart from that there are few polygons which are distinct from one another. The same data is being represented again in a different way, but now we see that there are lesser number of colors. As we can see, there's a blue, green, cyan, pink, and colors are there, and as well as red colors are there. So if I show this, then this gives the slightly more information. So in the information, extra slightly more information means that by looking at this, we can say that there are few polygons which look similar. So it means there are few values which are expected to be quite close to each other. And there are also a kind of grouping of the different polygons. So you're having a different groups of the polygons which are co-located. So it's there is a kind of cluster of those values which are also being represented. So it means so there is a slight improvement in the data representations compared to first one, where we see that the information is being represented and we also see some kind of grouping or other things are there. But what exactly this group is representing and so on, we are unable to decode. So for that, we need some kind of lookup table like this. In this case, a kind of legend is being provided. And over here, we see there are, okay, so these are the pink colors are being shown as a high, there's something is low, medium, and so on. So as we see it, then we can say, okay, there's something high, medium, low are there. And if I look into the data set, so this seems like even though it is a categorical data set, but the data set is having some kind of ordinality, like very low, low, high, medium, high, very high. So there are five. It can be arranged in those groups, or we can say that in particular orders. But the way the color has been chosen, that ordinality is not coming into play. So this says that there has to be some kind of an appropriate way of representing the thematic data sets. So to do that, we can do some kind of data transformation. So this is just an example where the to bring in the ordinality in our data sets. We're having a population density. These are the few numbers as we put in. So if you want to find out the values and where we see the lesser color or the tone which is darker is having a higher values, and tone which is having a lesser intensity is actually a lesser value. So as you see the increasing in tone, the corresponding value increases. So in this case, there are total 60 different tones or the colors has been used, and all these colors are actually in a ascending order. So it means like as the value increases, the corresponding darkness of the redness also increases. That's what we are seeing in this representations. And once we map this attribute data back to your spatial polygon, so it means like wherever we see a value, let's say for example around polygon number 10, which is around 4,000. And if you see that, so in that case, what we will, so correspondingly, all the 60 different polygons has been represented. But if you closely look into the cluster of these data sets, so what it seems is even though we are using 60 different colors, but broadly we can make out, okay, there are approximately 5 or 6 classes that mostly we can see that. For example, like these 3 polygons which we see, even though their tones are a bit different, but our eyes are not able to distinguish. So it looks like all of them are actually using the same color. Same is if I say these 3, these 2. So it's like the value over here, like these 3 polygons, and along with these 2 polygons, if you combine 5, 6, so all these are almost representing the same color and same value. So it means like all of them are having almost similar values. So in this case, we see that even though the ordinality in our data set, we are trying to build it by using different tones, but when we represent spatially, that distinction is not coming. And we are seeing that the overall 60 different tones are not there, but rather than 5 or 6 different groups of color, which is understood by the any map readers. So it means like we are using 60 colors we have provided in a lookup table, but not all of the colors is being used for the representations. So in some cases, what we need to do is we need to look for a kind of grouping of data set based on our distribution of the attribute information. So it means like we would like to group them together under the few conditions. So this is just an example which the classification is being applied to the attribute values. So as you can see that there are 5 different classes has been created from the histogram which is available for all these different polygons. So these attributes has been categorized into 5 groups. The range is being shown. Just an example is that the range is being shown over here. So in this case, as we see that if we look into the grouping, so it seems like there are few special, there are grouping of the informations at the attribute level. So it means that nearby values are having approximately same, and if the values or the classes from which the nearby values jumps to the another classes, so there has to have some kind of distinct characteristics. So these distinct characteristic is being created using some kind of statistical methods. So this is just an example of natural break. So natural break basically means that if you're having multiple groups in your data set, if you expect, in those cases, we can look for a natural break. For example, let's say this is a whole city, and I have done some kind of survey that what is the per capita expenses in each of these administrative areas. So in that case, what may happen is I would like to know, is it that all the different 60 places or 60 different wards are having a separate spending pattern? So it means like each of the polygons, the value is not linked to the nearby values, or is there some kind of distributions or some kind of relationship especially is also existing between them? So in those cases, we can look for a kind of histogram, natural break classification techniques, which will basically break the or create the class intervals in such a way that in each of the categories or in each of the basically bins, the number of data value which you see follows almost same group. So it falls almost on the same group. So the value in the neighboring groups will be different. So the histogram which will look like for a particular group will be different from the histogram from the other group. And this basically is called a natural breaks. Generally, it's being applied or implied, it's being applied in the cases where we expect that in your data set, there are few natural groupings are there. So we want to say, okay, there's a low income group, high income group, there's a higher expenditure area, there's a lower expenditure areas, or the expenses in a particular administrative boundaries. So if you expect such kind of things to be existing, in those cases, the natural break classifications can be used. Then there are also another classification techniques, which is basically called equal interval. So what it means is that your whole range of your data set are divided in equally. So in this case, what we see is that the data sets are being grouped in together on the basis of ranges. And in such cases of equal interval, what happens is that the number of polygons with the same class will be equal. So it means like if in this case we are having a total 60 different values. So in each of these class interval, there are 15 different values are expected to be present in each of these classes, or the range, the total range will be divided into in such a way that the ranges between them are actually having an equal value. So in this case, we see that the first bucket is having a largest number of values or the groups of the polygons, which is falling within this range. So this shows that in the other values, like in the extreme fifth class, we see a very less number of polygons existing. So in that case, we see that the total color table, whatever we see, is not being effectively used, and in some cases, some colors are used, some color table values are used, overused compared to the other cases. But generally, it's been used in cases of temporal comparisons. In those cases, we would like to find out relative comparison within that. In those cases, equal intervals can be used. Then there are another classification technique, which is called a quantile base. So it's basically a percentile base. So let's say if you're having a total 5 classes, so it means like total 100 divided by 5. So 20% of the first first classes will fall within this group. So that is being done. So in this case, 20 and another 20 values and so on. So those kind of classification is being carried out, and based on the quantile values is being represented. So again, this is basically dependent upon the quantile is being created based on the values which is being represented, attribute values, not on the attribute numbers, but rather than the value of attribute. The first 20% of the total range is being divided into 20%, and within that it should fall. Then there's a standard deviation based classification technique, so which tells that how many of the classes are actually away from mean standard deviation 1 and 2 and so on. So this basically gives the kind of disparity. So it means that if I want to compare like in the lighter and darker tones, so this basically says that these areas are quite opposite apart. Mostly it is being represented or used for bringing out the disparity even though the average values are there. Just an example of that is that if you're having a country level GDP values, average values, and you're having different administrative areas like council or maybe the state level data sets available within a country, again in terms of GDP or per capita GDP, then if you want to say that, okay, there are a few state or counties which is having an per capita GDP quite high compared to others. So it's kind of that kind of disparity when you want to bring out, you can do that. Same way can be do with the help of some indicators like access, educations, accessibility, and so on. So these kind of socioeconomic indicator disparity, if you want to show, the standard deviation techniques classification is one of the way to do that. Then we are having another technique which is called a geometrical intervals. Again, instead of taking a mean and standard deviations, we take mean values, and correspondingly the geometrical interval is being created. So it basically gives, especially in your histogram, if you expect your data sets to be not normally distributed, but geometrical distributions are there, then in those cases the geometrical interval will be a better tool compared to the standard deviation based classification techniques, and it can give you classifications of the data sets. So if you see that in all these thematic mapping cases, we have to do some kind of grouping of the classifications. The main reason for that is basically to improve the readability of your maps. So generally it is being told that for a normal human being, if there are 8 sets, especially 8 sets are there, the same color, so people can distinguish between them in the 8 different shades of the same color quite easily. But if you increase the number of shades, now there are few other superhuman beings which who can differentiate even 20 shades colors. But in general, as you start increasing the number of shades from 8 to 9, 10, and so on, then people get a difficulty in distinguishing on the different shades of the same color. So in that case, it's like if you want to improve the readability of the maps, so you have to group your data set in such a way that people can see those groups individually. So considering them that these are actually representing a unified attribute. At the same time, they also need to look into a representation. The classification also needs to be chosen in such a way that it distinguishes one class to the another class. The impact of these classification and grouping is that you lose accuracy. So detailed values or individual values now is getting merged into your classes. So means your data set are now you are losing the accuracy, but at the same time you're also increasing the generalization. So it's a kind of trade-off, like how many classes you want, and based on that, how many grouping, what level of grouping you need to have it. That kind of trade-off always we need to deal with. Along with that, the purpose of your map representation. So, do you want to represent similar values? Do you want to represent multiple groups, individual multiple groups, or you want to show the disparity? So, based on the classification of the objective of your representation of your data sets, you can look for a kind of appropriate uh, classification techniques. But in most of the cases, generally we deal with how many classes and what are the meaningful way of classifying the data sets. So generally, if you want to do a classification, how many classification or data or the classes which we need. So we have to understand that if you're having a very less number of classes, then you cannot observe any pattern. So if I just create one class, put all the polygons into a same class, then there will not be any way to distinguish. So it means like there's no pattern will come. If you're having a two, if the number of classes is very high, then as I was telling, it becomes difficult to interpret in terms of grouping of a maps, then it will be difficult to comprehend in this as well. So this is basically generally we restrict to have 4 to 5 classes in general. If you are not looking for specific purpose classification scheme, then just on the basis of initial classification scheme, 4 to 5 classes is to be considered to be most convenient for almost all the human beings. And that's why most of the default GIS classification scheme will allow to classify your data set in 5 different classes. So just to summarize that in case of manual classifications, we create a manual classes, equal interval, we ignore the complete data distribution, but rather than simply based on the range, we create reported data sets. And the natural breaks are basically creating the subclasses. The quantile is being taken based on the quantile and standard deviations. So let's see once you carry out these processes and we understood that how the classification is done. So let's see the comparison of those classifications which is being done in different cases. So like if you want to have equal interval, so you're classifying your data sets, the corresponding impact is also will be visible in your maps. So like if you see the comparisons of equal interval, quantile, and then natural breaks, standard deviations, and so on. So if you carry out those classifications in a different ways of classifications, then what we observe is the spatial representation of all these information also differs. So like in this case, for example, in case of standard deviations, we see that in total in this case is around 8 different classes are there. So in that case, we can see that there are few special grouping of the informations are available in cases like which is at 3 standard deviations apart from each other. And we can also look into the cases that even in the close proximities, there are basically the few of the polygons which is quite apart. So it means like there are different values across, or the two different pole of the same information is existing, and they are even though they are especially co-located. So we can look into the cases. Why is it so? So is there any kind of physical barrier or some other reasons that there is even the data set is closely located, but their values are quite. Sometimes if you want to look for a kind of grouping, for example, in this case, the quantile-based classifications, what we see is that the top 20% are actually quite closely knit. There are very less number of polygons which are outside this cluster. So it means like on the western side, we are seeing a large amount of clusters compared to eastern or other areas. Where in the middle, we are seeing the least values again. The lowest values are grouped together quite heavily in the in this region. So it's basically also tells that top 20. So let's say if this data set represents a population density or per capita income, then we can say, okay, the top 20% riches are living near to the lower 20% of the strata. So that's kind of information we can get it. So if you're looking, if you want to find out strata based on percentile, and if you want to see grouping of all those data sets, are they grouped together? Because if there are grouping are there, then it means that there is a fundamentally some structural problem. So in that case, we can look for some kind of deviations or some specific explanation of that why these groupings are there. If you want to bring out the natural break and clusters, so it means that there are few histogram on the basis of histogram, we are seeing a few clusters quite closely located. So it also represents that the histogram or the spatial information on the histogram is also closely linked to spatial. So it means like whatever the association, grouping, disparity which we are seeing in histogram, that is also applicable on the spatial domain as well. So it means like there are few spatial processes or phenomena where we can make few interventions to make things better. So if you want to decide which of the method to apply in general, what we have to look for is that this would appropriately look for a data distribution. So this data distribution, what we do is we take a distribution of your data sets in such a way that it gets sorted out to values. That's what the histogram is being represented. So this represents a kind of cumulative distribution of the whole data sets, and it has to have from lower values to higher values. And then we should compare the theoretical aspect of the cases. So if this histogram distribution is a kind of represented in such a way that it's in the linear fashions, like in this case, is a linear fashion increasing. So all those histogram is if it is approximately near to the straight lines, then in that case, basically the straight line or equal interval classification technique is good. So that can be used for the classification. So this is basically on the basis of your data representations. If your data set is completely normally distributed, so it means like your in a cumulative graph, you will see that your representation of the data set is actually a kind of S or basically inverted S, you will see. So in that case, then you can expect that your data set is expected to be looked at as a standard normal distributions from that perspective. So in that case, you can look for a quantile based distributions technique can also be used if you are further looking into top 20, top 30, because normal distributions and combined with if your histogram is normally distributed, and if you do a quantile based classification, so they are automatically bringing out into top first 20, next 20, and so on. So those kind of informations can easily be looked into. And then once we do this classification, then you see that there's a spatial cluster or not. And based on that, we can look for a few spatial phenomena. Why is it so? It is a specific cluster or not. If you're having a kind of suppressions, or if you're having a kind of concave histogram, where it starts from the lower values, goes into concave, and it's kind of like this, then in those cases, then it means like it is basically starting from lower values to higher values, and in between there are different kind of means is expected. So if this deviation from the standard line is quite low, then in those cases, arithmetic mean based classifications can be used. Or if you're having a quite large, especially like in these kind of distributions, you may observe in rainfall and other things like that. So in those cases, you can use the geometrical mean. Similarly, if you see a sudden drop and sudden increase and are lost in most of the data set and few places you see that it is near to the largest values, then in those cases we can say that we can use a reciprocal means and so on. And if we are not, and if you're seeing any one of these cases not exactly matching, then in those cases what we can do is there may be an irregular interval, so we can look for a few breaking of it into multiple segments. It means looking for a multiple natural breaks process, and then we can do a classification. In fact, this further goes like can do a further classification like if you do a natural breaks, then within the group again we can apply separate classification based on cumulative distribution of that class. So this is an important aspect where whenever we do any kind of analysis of classifications, so we should make sure that how we are going to create classes the data sets. So this is just an example when you apply all those classification principle and represent them, finally you have to annotate that informations with an appropriate map elements. So those map elements has to be put together to generate a complete thematic layer. So there are also a way to represent multiple attributes combined together with different visual structures. So this is just an example of that, where two different attributes, water and as well as area cover, both of them land cover and water cover, in compared to the total area is being represented. So this is basically bi-attribute, bivariate attribute data set is being represented in these cases. But we can also use some other visual structures to represent the similar kind of informations in thematic maps. So this is here. I'll just stop it. Today, basically, I try to show that map making process is not just restricted to making a few attribute data and representing and putting a result, but there are also a thought has to go at the back, how to classify what is basically the objective of representations, and based on the data set and as well as along with the objective of your representations, we can combine those informations to provide an appropriate mapping representations. So with this, I'll close the session. So after 2 minutes, again, we'll come back and we'll discuss the questions. Thank you.